Hello there and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Tonight, we're exploring stars in the most soothing way possible, focusing on the quiet, beautiful truths that make these distant suns so wonderfully calming to contemplate. We'll wander gently through stellar nurseries where new stars are born in silence. Discover how ancient light carries messages across impossible distances, and learn about the patient rhythms that govern stellar life. Some of what you hear might surprise you in the gentlest way possible, while other facts will simply wash over you like a warm tide, peaceful and reassuring. And if these soft explorations help you unwind at the end of your day, consider liking and subscribing to help others find this quiet corner of wonder too. Now let yourself get completely comfortable and let's begin this dreamy journey among the stars. Stars are born in the quietest places in the universe. Deep in the cold darkness between worlds, vast clouds of gas and dust drift silently through space for millions of years. These stellar nurseries, called molecular clouds, are so still and peaceful that temperatures drop to just a few degrees above absolute zero. Within these gentle giants, which can stretch for hundreds of light years, gravity works with infinite patience. Slowly, almost imperceptibly, tiny regions begin to gather more material, growing denser grain by grain, atom by atom. There's no violence here, no sudden bursts of energy, just the soft accumulation of matter responding to gravity's tender pull. Eventually, after countless eons of this quiet gathering, the center grows warm enough for fusion to begin, and a new star ignites. But even this moment of birth happens gradually, like a candle being lit in slow motion, bringing light to a corner of the universe that has known only darkness. The light from stars takes years to escape their own surface. When we think of starlight, we imagine it streaming instantly from the star to our eyes. But the photons that eventually reach us on Earth have been on an incredibly long journey that began deep within the star's core. A single photon created by nuclear fusion at the center of a star, like our sun, doesn't simply race to the surface. Instead, it begins what's known as a random walk, bouncing billions upon billions of times off atoms and electrons in the dense stellar interior. Each collision sends the photon in a new direction, sometimes deeper into the star, sometimes closer to the surface. This gentle, meandering journey through the star's layers can take anywhere from thousands to hundreds of thousands of years. By the time that photon finally emerges from the star's surface and travels the mere 8 minutes to reach your eye, it has already been wandering through stellar matter for longer than human civilization has existed. The starlight touching your face right now began its journey before the pyramids were built. Some stars pulse like gentle heartbeats across space. Not all stars shine with steady light. Throughout the galaxy, there are stars that brighten and dim in regular rhythmic patterns, like cosmic breathing or the slow pulse of a vast heart. These variable stars expand and contract in response to changes in their internal pressure and temperature. As they grow larger, they become cooler and dimmer. As they shrink, they heat up and shine more brightly. The cycles are remarkably consistent, some taking days, others taking months or even years to complete one full pulse. Astronomers have discovered that these stellar heartbeats are so reliable, they can be used as cosmic clocks, helping us measure distances across the universe. There's something deeply comforting about these rhythmic stars, scattered throughout the night sky, each one keeping its own steady time in the darkness. Binary stars dance together in space for billions of years. More than half of all stars in our galaxy don't live alone. They exist in pairs, orbiting around each other in graceful cosmic waltzes that can last for billions of years. Some binary pairs are so close they complete an orbit in just hours, while others are separated by distances so vast that one orbit takes millions of years. These stellar partners influence each other in beautiful ways. They can share material, with gas flowing in gentle streams from one star to its companion. Sometimes they eclipse each other from our perspective on Earth, creating predictable patterns of dimming and brightening. In the most intimate binary systems, the stars are so close that their outer atmospheres touch, creating a figure 8 shape of shared stellar material. These cosmic dance partners remind us that even in the vastness of space, companionship exists on the grandest scales. Red dwarf stars burn so slowly they could outlive the universe. The smallest stars in our galaxy are also the most patient. Red dwarf stars, which make up about 3/4 of all stars, burn their fuel so gradually and efficiently that they can shine for trillions of years. While massive stars race through their lives in just a few million years, red dwarfs take a different approach entirely. They're like cosmic tortoises, slow and steady, converting their hydrogen fuel into helium at such a leisurely pace that they barely change over cosmic time. A red dwarf that formed when the universe was young is still burning today, virtually unchanged. These gentle stars are so long-lived that none of them anywhere in the universe has ever died of old age. Every red dwarf that has ever been born is still shining somewhere, a testament to stellar patience and the beauty of taking things slowly. Stars create every element heavier than hydrogen and helium in their cores. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of these elements were forged in the heart of ancient stars through a process so gentle, it's almost meditative. Deep within stellar cores, where temperatures reach millions of degrees, atoms dance together in nuclear fusion. Hydrogen atoms join to form helium. Then helium fuses to create carbon, and carbon combines to make oxygen. This process continues up the periodic table, with each new element requiring higher temperatures and pressures to form. The creation happens slowly, over millions of years, as stars patiently build the chemical complexity that will eventually make planets and life possible. When these stars finally end their lives, they release these precious elements into space, seeding the galaxy with the materials needed for new worlds. Every atom in your body, except for hydrogen, was once part of a star's gentle alchemy. The surface of the sun is cooler than its corona. One of the most puzzling and beautiful mysteries about our nearest star is that its surface, called the photosphere, is actually much cooler than the ghostly atmosphere that surrounds it. The sun's surface reaches temperatures of about 5,500 degrees Celsius, which sounds incredibly hot until you learn that the corona, the sun's outer atmosphere, blazes at temperatures exceeding 1 million degrees Celsius. This seems to violate our everyday experience that things get cooler as you move away from a heat source. Scientists believe this heating happens through complex magnetic processes, where twisted magnetic field lines snap and reconnect, releasing energy into the thin corona. During a total solar eclipse, when the bright surface is blocked, you can see this superheated corona as a shimmering silver glow extending far into space. It's like a star wearing a crown of fire that burns hundreds of times hotter than the star itself. Neutron stars spin with impossible precision. When the most massive stars die, they sometimes collapse into objects so dense that a teaspoon of their material would weigh as much as a mountain. These neutron stars are only about 20 kilometers across, but they can spin hundreds of times per second, with timing so precise they rival the best atomic clocks on Earth. As these cosmic lighthouses rotate, they sweep beams of radiation across space like the beam from a lighthouse. When these beams point toward Earth, we detect regular pulses of radio waves, giving these objects their name: pulsars. Some pulsars have been observed for decades, and their pulses arrive with such reliability that astronomers use them to test theories of physics and even to search for gravitational waves. These spinning stellar remnants are so stable that they could keep better time than any clock we could build, ticking away in the darkness with mechanical perfection, born from gravitational collapse. Brown dwarfs are stars that never quite succeeded. Scattered throughout our galaxy are objects caught between being planets and stars, known as brown dwarfs or sometimes called failed stars. These cosmic in-betweens formed like stars from collapsing gas clouds, but they never gathered quite enough mass to sustain nuclear fusion in their cores. Instead, they glow dimly with leftover heat from their formation, slowly cooling over billions of years like cosmic embers. Brown dwarfs are surprisingly common, possibly outnumbering regular stars in our galaxy. They drift quietly through space, too small to shine like stars, but too large to be called planets. Some have been found with their own systems of orbiting worlds, creating strange solar systems where the central object glows only with the faint warmth of compression and time. They represent the universe's gentle failures, objects that almost became something else, but found their own peaceful existence in the space between definitions. White dwarf stars are cosmic diamonds cooling in space. When stars like our Sun reach the end of their lives, they shed their outer layers and leave behind their cores as white dwarf stars. These stellar remnants are incredibly dense, packing about as much mass as our Sun into a sphere roughly the size of Earth. The immense pressure inside these stars is so great that carbon atoms are squeezed into crystalline structures, essentially turning the entire star into a giant diamond. These stellar gems don't produce new energy through fusion. Instead, they simply radiate away their stored heat over billions of years, slowly cooling from white-hot to yellow to red to eventually becoming cold, dark objects floating silently through space. Some white dwarfs have been found to ring like bells when disturbed, creating stellar music as sound waves bounce through their crystalline interiors. They are the universe's way of creating the ultimate precious stones, diamonds the size of worlds, cooling quietly in the cosmic dark. The space between stars is filled with incredibly thin gas. What we call empty space between stars is actually filled with an extraordinarily thin mixture of gas and dust called the interstellar medium. This cosmic atmosphere is so tenuous that it contains only about 1 atom per cubic centimeter, making it 1 billion times thinner than the best vacuum we can create in laboratories on Earth. Yet this wispy material plays a crucial role in stellar birth and death. It provides the raw material for new stars, while also receiving the enriched gas expelled by dying stars. The interstellar medium has structure and texture, forming clouds, bubbles, and streams that flow through the galaxy. Some regions are heated by nearby stars and glow faintly, while others remain cold and dark. Solar wind from stars pushes against this material, creating vast cavities and shells. Though we can't see or feel this galactic atmosphere directly, it connects all the stars in our galaxy in a vast, breathing network of matter and energy. Stars form in groups, but most eventually drift apart. The stellar nurseries where stars are born typically create not just one star, but entire clusters containing hundreds or thousands of stellar siblings. These newborn stars begin their lives close together, all formed from the same giant molecular cloud, sharing similar ages and chemical compositions. For a while, they remain gravitationally bound in open clusters, moving through space together like cosmic families. But over millions of years, gravitational interactions and the influence of passing objects gradually disperse these stellar groups. Stars begin to drift apart, following different orbital paths around the galaxy's center. Eventually, most stars end up wandering alone through space, separated from their birth siblings by vast distances. Our own sun was almost certainly born in such a cluster billions of years ago, and somewhere in our galaxy, there may be other stars that share our sun's chemical fingerprint and age, distant relatives we may never identify among the billions of stars in the night sky. Thank you for joining me on this gentle journey through the realm of stars. We've drifted past stellar nurseries where new suns are born in silence, discovered the patient rhythms of variable stars, and learned about the cosmic diamonds that cool in space for billions of years. Each fact we've explored tonight carries within it a sense of the vast scales and gentle processes that govern stellar life. From the slow dance of binary companions to the precise timing of spinning neutron stars. As you continue to rest, remember that above you right now, countless stars are carrying out these quiet cosmic activities. Some are pulsing with steady heartbeats, others are slowly crystallizing into diamonds, and still others are beginning their billion-year journeys from stellar nurseries to the wider galaxy. The night sky is not empty or still, but filled with patient, ongoing processes that unfold over timescales that dwarf human experience. If you're still awake, there's more stellar wonder waiting in the next part of our exploration. And if these gentle astronomical truths help you find peace at the end of your day, consider subscribing to join our community of sleepy stargazers. Sweet dreams, and may your rest be as peaceful as the quiet spaces between the stars. The color of a star tells the story of its temperature. When you look up at the night sky, you might notice that not all stars appear the same color. Some shine with a brilliant blue-white light. Others glow with a warm golden hue, and still others emit a gentle red radiance. These colors aren't random decorations scattered across the heavens, but precise indicators of each star's surface temperature. The hottest stars burn blue, reaching temperatures of over 30,000 degrees Celsius, while the coolest red stars maintain a more modest 3,000 degrees. Our Sun, with its comfortable middle temperature of about 5,500 degrees, glows with that familiar yellow light that has warmed our world for billions of years. These stellar colors create a natural rainbow in the night sky, a cosmic spectrum where each hue represents a different chapter in the story of stellar physics. Some stars are so large they could contain our entire solar system. The universe is home to stellar giants so enormous they challenge our ability to comprehend their scale. Betelgeuse, one of the most famous supergiant stars, is so vast that if it replaced our Sun, its surface would extend beyond the orbit of Mars. These stellar titans are relatively rare, but when they do form, they dominate their cosmic neighborhoods. Their immense size comes at a cost, however. The larger a star grows, the more quickly it burns through its nuclear fuel. While our Sun will shine steadily for about 10 billion years, these supergiant stars race through their lives in just a few million years. They burn bright and large, creating spectacular displays in the night sky before ending their brief lives in explosion. Explosive supernova events that can be seen across vast distances. Their size is both their glory and their doom. A reminder that in the universe, bigger isn't always better for longevity. Cool stars can have planets in their habitable zones for hundreds of billions of years. Around the smallest and coolest stars in our galaxy, something remarkable happens to the concept of planetary habitability. These red dwarf stars burn so slowly and steadily that any planets orbiting in their habitable zones could potentially remain warm enough for liquid water for hundreds of billions of years. This is a time span so long that it dwarfs the entire age of our current universe. While planets around hot, massive stars have only a few million years before their host star dies, worlds orbiting red dwarfs could see countless civilizations rise and fall, entire evolutionary chains unfold, and biological processes that we can barely imagine. These patient stellar systems offer the universe's longest opportunities for the development of complex life, stretching the possibilities of biology across timescales that make Earth's few billion years seem like a brief moment. Stars sometimes steal material from their companions in beautiful spirals. In binary star systems, where two stars orbit close to one another, a graceful form of stellar theft can occur. If one star expands as it ages, its outer layers can begin to flow toward its companion in a process called mass transfer. This stolen material doesn't fall straight down onto the receiving star. Instead, it forms an elegant spiral structure called an accretion disk, where gas orbits the star in ever-tightening circles before finally joining its new host. As this material spirals inward, friction heats it to incredible temperatures, causing it to glow brightly in various wavelengths of light. The process creates some of the most beautiful and complex structures in astronomy, with streams of glowing gas connecting one star to another like cosmic bridges. This stellar sharing can continue for millions of years, gradually changing both stars and creating spectacular displays visible across interstellar distances. The nearest star to Earth is so far away that our fastest spacecraft would take thousands of years to reach it. Proxima Centauri, our closest stellar neighbor beyond the Sun, lies about 4.25 light-years from Earth. While this might not sound like much in cosmic terms, the actual distance is almost incomprehensibly vast. If you could drive a car to Proxima Centauri at highway speeds without stopping, the journey would take about 45 million years. Even our fastest spacecraft, traveling at speeds of tens of thousands of kilometers per hour, would need roughly 75,000 years to make the trip. This enormous distance helps explain why the stars appear as mere points of light, despite being massive, brilliant suns. The scale of interstellar space is so grand that it serves as a natural barrier, preserving the mystery and wonder of distant stars while keeping them safely remote from our small world. Stellar winds from massive stars can sculpt entire regions of space. The most massive stars don't just shine brightly. They also blow powerful winds of charged particles into the space around them. These stellar winds, moving at speeds of thousands of kilometers per second, are so intense they can carve out enormous bubbles in the surrounding interstellar medium. Over millions of years, these winds sweep away gas and dust, creating cavities that can span dozens of light-years across. When the wind encounters denser regions of material, it can compress them, sometimes triggering the formation of new stars along the edges of these stellar-carved bubbles. The most massive stars essentially reshape their cosmic neighborhoods, clearing out vast volumes of space while simultaneously preparing the conditions for future star formation. They are cosmic sculptors, using wind instead of tools to carve meaning into the raw material of space. Ancient starlight carries messages from the early universe. When we observe very distant stars, we're not just seeing them as they appear today, but as they existed long ago. Light takes time to travel across space, so the more distant a star is, the further back in time we're looking. Some of the stars we can detect with our most powerful telescopes are so far away that their light began its journey when the universe was young and very different from today. These ancient photons carry information about stellar conditions, chemical compositions, and physical processes from epochs when galaxies were still forming and the cosmos was more chaotic than it is now. By studying this old starlight, astronomers can piece together the history of stellar evolution and understand how the first generations of stars enriched the universe with heavy elements. Each ancient photon is like a message in a bottle, cast into the cosmic ocean billions of years ago, and only now washing up on our telescopic shores. Some binary stars are so close they share the same outer atmosphere. In the most extreme binary star systems, two stars can orbit so closely that they actually touch, sharing a common envelope of stellar material. These contact binary systems create a single figure-8 shaped structure where the two stellar cores remain distinct, but their outer layers merge into one continuous atmosphere. Material flows freely between the two stars, and they rotate together as a single unit while maintaining their separate nuclear burning cores. These intimate stellar partnerships are relatively short-lived by astronomical standards, lasting only a few million years before one of several dramatic endings occurs. They might merge completely into a single, more massive star, or one component might explode as a supernova. Contact binaries represent the ultimate stellar intimacy. Two separate stars choosing to live as one for a brief but brilliant cosmic moment. Cool brown dwarfs can have weather patterns and atmospheric storms. Despite being failed stars, brown dwarfs maintain surprisingly dynamic atmospheres, complete with weather systems that would make meteorologists envious. These objects, too small to sustain nuclear fusion but larger than planets, can have atmospheric temperatures ranging from hundreds to thousands of degrees. Within these hot atmospheres, clouds of exotic materials like iron and silicate particles can form and dissipate in complex weather patterns. Some brown dwarfs show periodic changes in brightness as storm systems rotate in and out of view, creating a kind of stellar meteorology. The atmospheric dynamics on these objects can include jet streams, cyclonic storms, and cloud bands that circle the entire object. Studying brown dwarf weather helps astronomers understand atmospheric physics under conditions impossible to recreate on Earth, providing insights into both stellar and planetary atmospheric science. The core of a dying star can collapse in less than a second. When a massive star finally exhausts its nuclear fuel, the end comes with stunning suddenness. The star's core, no longer supported by the outward pressure of fusion reactions, collapses catastrophically under its own gravity. What was once a core, the size of Earth, shrinks to a sphere only 20 kilometers across in less than 1 second. During this brief moment, matter is compressed to densities so extreme that protons and electrons are crushed together to form neutrons. The collapse releases an enormous amount of energy, sending shock waves racing outward through the star's outer layers and triggering the spectacular explosion we call a supernova. This cosmic implosion happens so quickly that if you could somehow watch it occur, the collapse would be finished before you could blink your eyes. It's one of the most dramatic and rapid transformations in the natural world, changing a star into something completely different in the span of a human heartbeat. Some stars are magnetic powerhouses, with fields trillions of times stronger than Earth's. Among the most extreme objects in the universe are magnetars, neutron stars with magnetic fields so powerful they defy easy comprehension. Earth's magnetic field, strong enough to deflect harmful cosmic radiation and guide compass needles, would seem laughably weak next to these stellar magnetic monsters. A magnetar's magnetic field is so intense it could erase the data from every credit card on Earth from a distance of thousands of kilometers. These fields are strong enough to distort the shapes of atoms themselves and can cause the solid crust of the neutron star to crack and shift, releasing bursts of energy that can be detected across the galaxy. Magnetars represent nature's most powerful magnets, created in the extreme conditions of stellar collapse and maintained by the incredible rotation and density of neutron star matter. They are cosmic generators operating on a scale that makes human technology seem primitive by comparison. Double stars can create some of the most spectacular explosions in the universe. In certain binary systems, a white dwarf star can gradually accumulate material stolen from its companion until it reaches a critical mass threshold. When this happens, the white dwarf undergoes a thermonuclear explosion called a type Ia supernova, briefly shining with the brilliance of billions of suns. These explosions are so consistent in their peak brightness that astronomers use them as standard candles to measure distances across the universe. The explosion completely destroys the white dwarf, scattering its material and the stolen matter from its companion across space at speeds of thousands of kilometers per second. These binary-driven supernovae are some of the most important events in cosmic history, responsible for creating and distributing many of the heavy elements essential for planet formation and life. They represent the ultimate sacrifice of stellar companionship, where one star's generosity eventually leads to both partners' destruction in a blaze of cosmic glory. Young stars are often surrounded by disks where planets might be forming. When stars are born from collapsing gas clouds, they typically don't use up all the available material in their formation. The leftover gas and dust settles into a rotating disk around the young star, creating what astronomers call a protoplanetary disk. Within these cosmic construction zones, the same processes that formed our own solar system billions of years ago are happening right now. Dust particles stick together to form larger and larger objects, eventually growing into asteroids, comets, and planets. These disks can persist for millions of years, gradually clearing out as material either falls into the star, gets blown away by stellar winds, or becomes incorporated into newly formed worlds. Observing these stellar nurseries gives us glimpses into our own cosmic origins and helps us understand how common planetary systems might be throughout the galaxy. Each young star surrounded by a disk represents a potential solar system in the making, a cosmic construction project that might one day harbor worlds and perhaps even life. Giant stars end their lives by creating the seeds of future worlds. When the most massive stars reach the end of their brief but brilliant lives, they don't simply fade away quietly like smaller stars. Instead, they explode in supernovae so powerful they can be seen from billions of light years away, briefly outshining entire galaxies. But these cosmic fireworks serve a greater purpose than mere spectacle. During the violent moments of a supernova explosion, the extreme temperatures and pressures create elements that cannot be forged in the normal burning of stellar cores. Gold, silver, platinum, and uranium are born in these stellar death throes, along with dozens of other heavy elements essential for rocky planets and complex chemistry. The explosion hurls these newly minted elements into space at tremendous speeds, seeding the surrounding interstellar medium with the raw materials needed for future generations of stars and planets. Every supernova is both an ending and a beginning, a stellar death that enriches the galaxy with the chemical diversity necessary for worlds like Earth to eventually form. Some stars appear to twinkle because of our own atmosphere. The gentle twinkling of stars that has inspired poets and dreamers throughout human history isn't actually caused by the stars themselves. This beautiful effect occurs entirely within Earth's atmosphere, as starlight passes through pockets of air with slightly different temperatures and densities. These atmospheric variations act like a constantly shifting lens, bending the starlight back and forth in subtle ways that make the star appear to flicker and dance. Planets, being much closer and therefore appearing larger in our sky, don't twinkle as much because their light comes from a broader area that averages out these atmospheric effects. lights. The twinkling is most pronounced when stars are low on the horizon, where their light must pass through more of our atmosphere to reach our eyes. This atmospheric effect serves as a gentle reminder that we observe the cosmos through the filter of our own world, and that even our home planet plays a role in shaping the beauty we see in the night sky. Variable stars helped us discover the true scale of the universe. Among the most important stars for understanding cosmic distances are a special class of variable stars called Cepheids, named after the constellation where the first one was discovered. These stellar lighthouses pulse with such regular periods that astronomers realized their pulsation rate is directly related to their true brightness. By comparing how bright a Cepheid appears from Earth with how bright it actually is, astronomers can calculate its distance with remarkable precision. This relationship, discovered by astronomer Henrietta Swan Leavitt in the early 20th century, became one of the most powerful tools for measuring distances across the galaxy and beyond. Cepheid variables helped us realize that many fuzzy patches in the night sky were actually other galaxies far beyond our own Milky Way, fundamentally changing our understanding of the universe's scale. These pulsing stars became the cosmic yardsticks that revealed just how vast and populated the universe truly is. Star formation creates beautiful glowing nebulae that can last for millions of years. When massive young stars begin shining in stellar nurseries, their intense ultraviolet radiation has a remarkable effect on the surrounding gas and dust. This energetic light strips electrons from hydrogen atoms in nearby clouds, causing the gas to glow with a characteristic red light. These illuminated regions, called emission nebulae, create some of the most stunning and colorful objects in the night sky. The Orion Nebula, visible even with small telescopes, is perhaps the most famous example of star formation in action. These glowing stellar maternity wards can span dozens of light years across and continue shining for millions of years, as long as the young stars within them keep producing ultraviolet radiation. Each nebula is unique, shaped by the stellar winds and radiation of its embedded stars into delicate structures that resemble flowers, butterflies, or abstract cosmic art. They remind us that star birth is not just a violent process of gravitational collapse, but can also create regions of ethereal beauty that glow softly in the darkness of space. The oldest stars in our galaxy contain almost no heavy elements. Deep in the halo surrounding our Milky Way galaxy, astronomers have found ancient stars that formed when the universe was very young and chemically simple. These stellar time capsules contain almost none of the heavy elements that are common in younger stars like our Sun. Their atmospheres are composed almost entirely of hydrogen and helium, the two lightest elements that were created in the Big Bang itself. The near absence of heavier elements tells us these stars formed before many generations of stellar death had enriched the galaxy with the products of nuclear fusion and supernova explosions. Studying these primitive stars gives astronomers a window into the very early universe, when the first stellar generations were just beginning to light up the cosmic dark. They are living fossils, ancient survivors from a time when the galaxy was young and the periodic table was almost empty. Their simple chemistry is a reminder of how the universe has grown more complex over time. as stars have gradually built up the rich diversity of elements we see today. Some stars orbit around empty space in invisible partnerships. Throughout the galaxy, astronomers have discovered single stars that seem to be dancing with invisible partners. These stars move in regular orbital patterns, speeding up and slowing down as they circle around apparently empty regions of space. The invisible companions are often white dwarf stars, neutron stars, or even black holes that emit little or no visible light, but still exert gravitational influence on their stellar partners. By carefully measuring the visible star's orbital motion, astronomers can determine the mass and characteristics of the unseen companion, revealing a hidden population of dark stellar remnants scattered throughout the galaxy. Some of these systems periodically transfer material from the visible star to its compact companion, creating brief flares of light as the stolen matter heats up during its final plunge. These cosmic partnerships remind us that much of the universe's matter exists in forms we cannot directly see, detectable only through their gravitational effects on the objects around them. Stellar collisions can create entirely new types of stars. In the dense cores of globular clusters, where hundreds of thousands of stars are packed into a relatively small volume, direct stellar collisions occasionally occur despite the vast distances typically separating stars. When two stars actually crash into each other, the result can be a completely new kind of stellar object that couldn't form through normal stellar evolution. These collision products, sometimes called blue stragglers, appear younger and more massive than they should be based on the age of their stellar cluster. The violent merger rejuvenates the combined star, giving it a new lease on stellar life and allowing it to burn brighter and longer than either of its parent stars could have alone. Some collisions create exotic objects like helium stars or stripped stellar cores that follow evolutionary paths unknown in normal single-star evolution. These cosmic car crashes are rare but important events that add diversity to the stellar population and create objects that challenge our understanding of how stars live and die. The space around hot stars is carved into glowing cavities by stellar winds. The most massive and hottest stars don't just shine passively into space. They actively reshape their cosmic neighborhoods by blowing powerful stellar winds that can move at speeds of several thousand kilometers per second. These winds carry away significant amounts of the star's mass over its lifetime, while also pushing against the surrounding interstellar medium like a cosmic snowplow. Over millions of years, these stellar winds carve out enormous bubble-shaped cavities in the gas and dust around the star, creating structures that can span dozens of light-years across. The edges of these wind-blown bubbles often glow brightly where the fast-moving stellar wind collides with slower-moving interstellar material, creating shock waves that heat the gas to thousands of degrees. These stellar wind bubbles are some of the largest structures created by individual stars, demonstrating how even objects separated by vast distances can influence and reshape the space around them. Cool red giant stars can pulsate with periods lasting several years. As stars age and evolve beyond their main sequence lifetime, many enter a phase where they expand into cool, luminous red giants. Some of these elderly stars develop a tendency to pulsate, growing larger and smaller in cycles that can last months or even years. During their expansion phases, these stars become cooler and redder, while their contraction phases make them somewhat hotter and bluer. The pulsations are driven by changes in the star's internal structure, as it struggles to maintain equilibrium during its later evolutionary stages. These long-period variable stars can change in brightness by factors of hundreds or even thousands over the course of their pulsation cycles, sometimes becoming visible to the naked eye during their bright phases and then fading beyond the reach of small telescopes during their dim phases. Their slow, rhythmic variations add a temporal dimension to stellar observation, reminding us that stars are dynamic objects that change not just over millions of years, but on timescales we can actually observe within human lifetimes. Multiple star systems can create complex gravitational choreographies. While binary star systems are common throughout the galaxy, nature sometimes creates even more elaborate stellar arrangements. Triple star systems, where 3 stars orbit around their common center of mass, create intricate gravitational dances that can persist for billions of years. Some of these systems consist of a close binary pair orbited by a distant third star, while others have all 3 stars in more complex, interweaving orbits. Even more exotic are systems with 4, 5, or even 6 stars, all gravitationally bound together in stable configurations. These multiple star systems challenge our understanding of orbital mechanics and create environments where planets, if they exist, would experience wildly variable conditions as different stars rise and set in complex patterns. The gravitational interactions between multiple stars can also lead to dramatic events when one star's evolution affects its companions, potentially leading to stellar mergers, mass transfer episodes, or the ejection of one star from the system entirely. Dying stars can create planetary nebulae that glow for thousands of years. When stars similar to our Sun reach the end of their lives, they don't explode in violent supernovae, but instead undergo a more gentle transformation. These aging stars gradually shed their outer layers in a series of stellar exhalations, creating expanding shells of glowing gas around the remaining stellar core. Despite their name, planetary nebulae have nothing to do with planets. They earned this misleading designation because early astronomers thought their round, disc-like appearance resembled planets when viewed through small telescopes. The central white dwarf star provides the ultraviolet radiation that causes the expelled gas to glow in beautiful colors, creating some of the most photogenic objects in the night sky. Each planetary nebula is unique, shaped by factors such as the star, air's rotation, magnetic field, and whether it had a binary companion. These stellar memorials can persist for tens of thousands of years before the expanding gas becomes too diffuse to glow brightly, serving as temporary monuments to stars that lived and died in relative peace. Some stars are born already spinning at tremendous speeds. While most stars rotate sedately, completing one rotation every few days or weeks, some stars are born spinning so rapidly they complete a full rotation in just a few hours. These fast-spinning stars are often flattened into oblate shapes by their rapid rotation, bulging outward at their equators like cosmic spinning tops. The most extreme cases spin so quickly They approach the theoretical limit where centrifugal force would overcome gravity and tear the star apart. Fast rotation affects many aspects of a star's life, from its magnetic field generation to its stellar wind properties and even its evolutionary timeline. Some rapidly rotating stars throw off material from their equatorial regions, creating circumstellar disks of gas and dust that can persist for millions of years. The rotation rate of a star often depends on its formation history, with stars that formed from rapidly rotating gas clouds or experienced close encounters with other stars, encounters with other objects, retaining high spin rates throughout their lives. Binary systems sometimes create cosmic lighthouses that sweep the galaxy. In some binary star systems where one component has evolved into a compact neutron star, the system can become a cosmic lighthouse that sweeps beams of radiation across the galaxy. As the neutron star accretes material from its companion, this matter spirals inward and heats to millions of degrees before finally reaching the neutron star's surface. The intense magnetic field of the neutron star can funnel this hot material toward its magnetic poles, creating beams of X-rays and other high-energy radiation that sweep across space as the star rotates. From Earth, we observe these systems as regular pulses of radiation, earning them the name X-ray pulsars or millisecond pulsars, depending on their pulse period. These binary lighthouse systems can be detected across vast distances and provide unique laboratories for studying matter under the most extreme conditions in the universe. They demonstrate how stellar evolution and binary interactions can create some of the most energetic and precisely timed phenomena in the cosmos. Massive stars create their own stellar graveyards before they die. The most enormous stars in the universe don't wait until death to begin shaping their final resting places. Throughout their brief but intense lives, these stellar giants blow away the gas and dust around them with such force that they create vast, empty cavities in space. When the star finally explodes as a supernova, the blast wave encounters this pre-cleared region and expands into it more easily than it would into dense interstellar material. This creates supernova remnants with distinctive shapes and characteristics, often forming beautiful, symmetrical shells of glowing gas that can persist for thousands of years. The star essentially excavates its own tomb, ensuring that when it dies, its final explosion will have room to expand and create one of the most spectacular light shows into the galaxy. These stellar preparations remind us that even cosmic death can be an act of creation, transforming violent endings into luminous memorials that enrich the space between stars. Some binary stars trade places over millions of years. In certain binary systems, a fascinating role reversal can occur over cosmic timescales. Initially, the more massive star evolves faster and begins to transfer material to its smaller companion. As this process continues over millions of years, the originally smaller star can actually become more massive than its partner. Eventually, the roles completely reverse, with the formerly less massive star becoming the dominant member of the pair. This stellar dance of changing identities can happen multiple times in a single system's lifetime, creating complex evolutionary histories that challenge astronomers to piece together each system's past. Sometimes this mass exchange leads to exotic stellar types that cannot form through normal single star evolution, creating objects that exist only because of their binary nature. These systems demonstrate that stellar partnerships are not static arrangements, but dynamic relationships that evolve and change over the vast stretches of cosmic time. The atmospheres of cool stars can contain clouds made of minerals. In the outer atmospheres of the coolest stars, temperatures drop enough for unusual cloud formation to occur. Instead of water vapor like Earth's clouds, these stellar atmospheres can develop clouds composed of minerals like iron, magnesium, and silicon compounds. These exotic clouds form high in the star's atmosphere, where temperatures are cool enough for these normally solid materials to condense into tiny particles. As these mineral clouds move through the stellar atmosphere, they can affect the star's brightness and color, creating variations that astronomers can detect from Earth. Some of these clouds are so dense they can significantly dim the star's light, while others create subtle spectral features that reveal their composition. The presence of these mineral clouds gives cool stars their distinctive red color and affects how they lose mass through stellar winds. It's a reminder that the familiar physics of cloud formation extends far beyond Earth, creating weather patterns in stellar atmospheres using materials that would be exotic by terrestrial standards. Young star clusters gradually dissolve into the galaxy like sugar in cosmic tea. When groups of stars are born together in stellar nurseries, they initially remain close to one another, bound by their mutual gravitational attraction. These open star clusters can contain anywhere from dozens to thousands of stellar siblings, all roughly the same age and chemical composition. However, over time, the cluster begins to evaporate as individual stars gain enough energy to escape the group's gravitational well. This process happens slowly, over hundreds of millions of years, as gravitational interactions between cluster members and encounters with passing interstellar clouds gradually steal away the cluster's stars. Eventually, what began as a tight grouping of stellar siblings becomes scattered throughout the galaxy, with former cluster members following independent orbital paths around the galactic center. Our own sun was likely born in such a cluster billions of years ago, and its stellar brothers and sisters are now spread across thousands of light-years of space, indistinguishable from the general stellar population, except for subtle similarities in age and composition. Stellar magnetic fields can create spectacular eruptions visible across interstellar distances. Some stars possess magnetic fields thousands of times stronger than our sun's, and these powerful magnetic structures can become twisted and tangled by the star's rotation and internal motions. When these magnetic field lines become too stressed, they can suddenly snap and reconnect in violent events called stellar flares. These magnetic explosions release enormous amounts of energy in just minutes or hours, temporarily increasing the star's brightness by factors of hundreds or thousands. The largest stellar flares release more energy than our sun produces in an entire year, hurling charged particles into space at tremendous speeds. Some flare stars are so active they experience dozens of these magnetic outbursts every day, creating a constantly changing display of stellar violence. These events provide natural laboratories for studying magnetic field physics, under conditions far more extreme than anything possible on Earth, helping astronomers understand how magnetic fields behave in the most energetic environments in the universe. Carbon stars create soot in space like cosmic chimneys. During certain phases of stellar evolution, some aging stars develop atmospheres rich in carbon, creating conditions similar to a sooty candle flame, but on a stellar scale. These carbon stars burn their remaining fuel in a way that produces more carbon than oxygen in their outer layers, leading to the formation of carbon-based molecules and tiny particles of graphite and other carbon compounds. This cosmic soot gets blown away from the star by stellar winds, seeding the surrounding interstellar medium with carbon-rich dust grains. Over the star's lifetime, it can produce and distribute enormous quantities of these carbon particles, contributing significantly to the dust content of the galaxy. Some of this stellar soot eventually becomes incorporated into new star-forming regions and planetary systems, providing the carbon-rich building blocks necessary for the complex chemistry of life. These stars are essentially cosmic chimneys, burning their fuel in a smoky process that enriches the galaxy with one of the most important elements for biological processes. The cores of massive stars become incredibly hot just before collapse. In the final moments of a massive star's life, its core reaches temperatures so extreme they dwarf even the nuclear furnaces that have powered the star for millions of years, as the star desperately tries to fuse heavier and heavier elements to maintain the outward pressure needed to support its enormous weight. Core temperatures can reach billions of degrees. At these incredible temperatures, the atomic nuclei move so quickly that they can overcome the electrical repulsion between protons and fuse into even heavier elements like iron and nickel. However, once iron forms in the core, the fusion process actually absorbs energy rather than releasing it, removing the star's last source of support against gravitational collapse. These ultra-hot stellar cores exist for only moments before gravity finally wins. But during their brief existence, they represent some of the most extreme thermal environments in the universe, rivaling the conditions that existed in the first moments after the Big Bang. Some stars appear to be moving backward through space relative to their neighbors. Among the billions of stars in our galaxy, astronomers have discovered unusual objects that seem to be swimming against the galactic current. These high-velocity stars move through space with speeds so different from their stellar neighbors that they stand out like cosmic salmon swimming upstream. Some of these stellar oddballs are moving so quickly they may eventually escape the galaxy entirely, becoming intergalactic wanderers. The unusual motions of these stars often reveal their exotic origins. Some may be survivors of binary systems where their companions exploded as supernovae, giving them a gravitational kick that sent them careening through space. Others might be visitors from smaller galaxies that were disrupted when they came too close to our Milky Way. These stellar outcasts provide clues about the violent events that can reshape stellar orbits and occasionally fling stars across vast distances at speeds that dwarf typical stellar motions. Wolf-Rayet stars are cosmic pressure washers stripping away their own atmospheres. Among the most extreme stars in the galaxy are objects called Wolf-Rayet stars. massive stellar giants that are literally blowing themselves apart through incredibly powerful stellar winds. These stars have lost their outer hydrogen layers, exposing their hot, helium-rich cores to space. The intense radiation from these exposed cores drives stellar winds so powerful they can reach speeds of several thousand kilometers per second, carrying away the equivalent of Earth's mass every year. These cosmic pressure washers create some of the most spectacular nebulae in the galaxy as their high-speed winds collide with previously ejected material, forming intricate shells and bubbles of glowing gas. Wolf-Rayet stars are thought to be the immediate precursors to some of the most energetic supernova explosions, making them crucial players in the chemical evolution of galaxies. Their self-destructive behavior enriches the surrounding space with heavy elements while creating beautiful, complex structures that can persist long after the star itself has vanished. The smallest stars are actually getting smaller as they age. Unlike most objects that expand as they heat up, the smallest stars in the universe actually contract and become denser as they burn their nuclear fuel. This counterintuitive behavior occurs because these low-mass red dwarf stars have a unique internal structure where their entire volume participates in the nuclear burning process. As they convert hydrogen to helium throughout their interiors, the average molecular weight of their material increases, causing the star to shrink under its own gravity. This contraction actually makes the star's core hotter and increases its energy output, causing these tiny stars to slowly brighten over their incredibly long lifetimes. A red dwarf that forms today will be significantly smaller and brighter billions of years from now, assuming the universe lasts long enough for us to observe such changes. This gradual stellar evolution means that red dwarf stars are not constant over time, but are slowly transforming themselves through the very process that keeps them shining. Stellar nurseries can trigger chain reactions of star formation across entire galaxy arms. When massive stars form in one region of a galaxy, their intense radiation and eventual supernova explosions don't just affect their immediate surroundings. The shock waves and energy they release can compress nearby gas clouds, triggering new episodes of star formation in neighboring regions. These newly formed stars, in turn, can trigger additional star birth in their vicinity, creating a propagating wave of stellar formation that can sweep across entire spiral arms over tens of millions of years. This process, called sequential star formation, helps explain why we see organized patterns of young stars in spiral galaxies rather than random distributions. Each generation of massive stars plants the seeds for the next generation, creating a cosmic relay race of stellar birth that can persist, for hundreds of millions of years. The beautiful spiral structure we see in galaxies like our own Milky Way is partly maintained by these chains of star formation, where each stellar generation helps ensure the continuation of the next. Some binary systems create their own planetary nebulae through stellar interaction. When two stars in a binary system evolve at different rates, their interaction can create some of the most complex and beautiful planetary nebulae in the galaxy. As one star expands into a red giant, it can transfer material to its companion, or the two stars can actually merge, creating conditions that lead to the ejection of intricate shells and streams of glowing gas. These binary-produced nebulae often show distinctive shapes, that reflect the orbital motion and mass transfer history of their parent stars. Some display elegant bipolar structures with jets and lobes extending in opposite directions, while others show spiral patterns frozen in the expanding gas. The gravitational influence of the binary system can focus the ejected material into specific directions, creating nebulae that look more like cosmic sculptures than the simple spherical shells produced by single aging stars. These systems demonstrate how stellar companionship can influence even the final acts of stellar evolution, turning the death of stars into elaborate artistic displays. The sound waves inside stars create their own form of stellar seismology. Just as earthquakes create seismic waves that reveal Earth's internal structure, stars experience their own form of acoustic oscillations that allow astronomers to probe their hidden interiors. These stellar sound waves are created by turbulent convection in the star's outer layers, generating pressure fluctuations that propagate through the stellar interior like sound waves through air. Different oscillation modes penetrate to different depths within the star, carrying information about the temperature, density, and composition of regions that can never be observed directly. By measuring tiny variations in a star's brightness and surface velocity caused by these oscillations, astronomers can map the internal structure of stars with remarkable precision. This technique, called astroseismology, has revealed details about stellar cores, rotation rates at different depths, and even the ages of individual stars. It's as if stars are constantly singing to us in frequencies we can measure, telling us stories about their internal lives through the music of stellar oscillation. Giant molecular clouds can birth thousands of stars over millions of years. The largest star-forming regions in our galaxy are vast molecular clouds that can span hundreds of light years and contain enough material to create thousands of new stars. These cosmic nurseries are not sites of sudden stellar birth, but rather regions where star formation proceeds gradually over millions of years in multiple episodes. Different parts of the cloud collapse at different times, creating a complex temporal sequence of stellar generations within the same general region. The first massive stars to form begin affecting their surroundings almost immediately, their radiation and winds creating bubbles and cavities that influence where subsequent stars can form. Over time, the cloud becomes a patchwork of stellar nurseries at different stages of evolution, with some regions just beginning to form stars, while others already host mature stellar populations. This extended star formation process means that what we call a single stellar nursery is actually a complex ecosystem where multiple generations of stars interact and influence each other's development across millions of years of cosmic time. The rotation of stars can be measured by watching their surfaces breathe. Many stars show subtle pulsations caused by acoustic waves bouncing around inside their interiors, creating tiny expansions and contractions of their surfaces. These stellar breathing patterns can reveal not only the star's internal structure, but also how quickly different parts of the star are rotating. Because stars are not rigid bodies, their cores often rotate at different rates than their outer layers, creating complex internal rotation profiles. By analyzing the frequencies of stellar oscillations with incredible precision, astronomers can map these rotation differences and understand how stars transport angular momentum between their cores and surfaces. Some stars show evidence of rapid core rotation left over from their formation, while others have cores that spin much more slowly than their outer layers due to magnetic braking effects. This stellar seismology allows astronomers to peer inside stars and observe rotational dynamics that would otherwise be completely hidden from view. Cool stars can maintain surface temperatures stable for billions of years. The smallest and coolest main sequence stars are remarkable for their thermal stability, maintaining nearly constant surface temperatures for timescales that dwarf the age of the universe. Unlike more massive stars that gradually heat up and change color as they evolve, red dwarf stars can burn at essentially the same temperature for hundreds of billions of years. This thermal constancy occurs because these stars mix their material so thoroughly that they use their nuclear fuel with incredible efficiency, burning hydrogen throughout their entire volume rather than just in a central core. The result is a stellar life cycle so extended and stable that any planets orbiting in the habitable zone of a red dwarf could expect consistent conditions for periods longer than the current age of the cosmos. This stellar steadiness makes red dwarf systems particularly interesting targets in the search for life, as they provide the ultimate in long-term environmental stability for any worlds that might exist in their gravitational embrace. Binary star systems can create some of the most precise clocks in the universe. When two compact stellar remnants orbit each other in tight binary systems, they create gravitational wave signals so regular they rival atomic clocks in their precision. These systems lose energy by radiating gravitational waves, causing their orbits to decay in precisely predictable ways, according to Einstein's theory of general relativity. The orbital decay is so regular that astronomers can predict the arrival time of radio pulses from these systems centuries into the future with remarkable accuracy. Some binary pulsar systems maintain timing precision better than 1 part in 100 billion, making them among the most precise natural clocks known to science. These stellar chronometers have been used to test fundamental physics, detect gravitational waves indirectly, and even search for evidence of gravitational wave background radiation left over from the early universe. They represent the ultimate marriage of stellar evolution and precision physics, where the death of two massive stars creates a cosmic timepiece of extraordinary accuracy. The chemical composition of a star's atmosphere tells the story of galactic evolution. Every star carries within its outer layers a chemical fingerprint that reveals not only its own evolutionary history, but also the history of star formation in its region of the galaxy. Stars that formed early in the galaxy's history show atmospheres dominated by hydrogen and helium, with only tiny traces of heavier elements. Younger stars, like our Sun, contain much higher abundances of elements like carbon, oxygen, and iron, created and distributed by previous generations of stars that lived and died before our solar system formed. By studying the chemical compositions of thousands of stars throughout the galaxy, astronomers can trace how different elements were created and dispersed over cosmic time. This stellar archaeology reveals patterns of galactic chemical evolution, showing how the Milky Way gradually enriched itself with heavy elements through billions of years of stellar birth, life, and death. Each star is essentially a chemical time capsule, preserving information about the conditions that existed when and where it formed. Some stars oscillate between different evolutionary phases multiple times. During certain stages of stellar evolution, stars can become unstable and oscillate between different configurations over periods of thousands of years. These thermal pulse stars alternate between phases of helium burning and periods of relative quiescence, creating dramatic changes in their size, temperature, and brightness. During the active phases, the star can expand to enormous dimensions and increase its luminosity by factors of thousands, while during the quiet intervals, it contracts and dims significantly. This stellar breathing can continue for hundreds of thousands of years, with each cycle lasting anywhere from a few hundred to several thousand years. The pulsations are driven by the complex interplay between nuclear burning, convection, and the star's attempt to maintain hydrostatic equilibrium during its later evolutionary phases. These oscillating stars represent some of the most dynamic objects in stellar evolution, constantly changing their fundamental properties as they struggle to maintain stability during their transition toward becoming white dwarf stars. The death of massive stars can trigger the birth of their own replacements. When a massive star explodes as a supernova, the shock waves it creates don't just disperse the star's material into space, but also compress nearby gas clouds in ways that can trigger new episodes of star formation. These compression waves can cause previously stable clouds to begin collapsing under their own gravity, initiating the formation of new stellar generations. In some cases, the supernova shockwave creates a ring or shell of compressed material around the explosion site, leading to star formation in a roughly circular pattern. Over millions of years, this process can create expanding rings of young stars centered on the location of ancient supernova explosions. The massive stars that triggered the initial L-star formation episode are long gone, but their influence persists in the form of the stellar populations they helped create. This process represents a form of stellar reincarnation, where the death of one generation of massive stars directly leads to the birth of the next generation, maintaining the cycle of stellar birth and death that drives galactic evolution. Stellar winds can carry the magnetic fields of stars far into space. Many stars, including our Sun, possess magnetic fields that extend well beyond their visible surfaces through the medium of stellar winds. These magnetized particle streams carry the star's magnetic field lines outward, creating vast magnetic structures that can influence the space environment around planets and other nearby objects. In binary systems, the magnetic fields carried by stellar winds can interact with companion stars, creating complex magnetic reconnection events and particle acceleration processes. Some stars with particularly strong magnetic fields and powerful winds can create magnetic structures that extend for several astronomical units, effectively magnetizing large volumes of space around them. These extended stellar magnetospheres can affect the formation and evolution of planetary systems, potentially stripping away atmospheric material from close-in planets or creating radiation environments hostile to life. The study of stellar magnetic fields and their interaction with stellar winds provides insights into space weather processes and helps astronomers understand how magnetic activity affects the habitability of exoplanetary systems. The cores of red giant stars can spin much faster than their outer layers. As stars evolve off the main sequence and expand into red giants, their internal structure undergoes dramatic changes that can lead to surprising rotational dynamics. While the star's outer envelope expands and slows down due to conservation of angular momentum, the core can actually speed up as it contracts and becomes denser. This creates a situation where the stellar core spins much more rapidly than the extended outer atmosphere, sometimes by factors of hundreds or thousands. The rapid core rotation can be detected through asteroseismology, as the spinning core affects the frequencies of acoustic oscillations that propagate through the star. This internal rotation differential has important consequences for stellar evolution, affecting how elements are mixed within the star and how angular momentum is transported between different layers. Some red giant stars show evidence of cores spinning so rapidly they approach the theoretical limits imposed by centrifugal forces, creating internal dynamics that are only beginning to be understood through detailed stellar modeling and observational studies. Multiple star systems can create complex tidal effects on any orbiting planets. In stellar systems containing 3 or more stars, the gravitational environment becomes incredibly complex, with planets experiencing constantly changing tidal forces as the different stars move through their orbital configurations. These varying tidal stresses can heat planetary interiors through friction, potentially creating geological activity on worlds that would otherwise be geologically dead. In some cases, the tidal heating can be so intense that it maintains liquid water oceans beneath icy surfaces, similar to what happens on some moons in our own solar system, but potentially on much larger scales. The complex gravitational dynamics of multiple star systems also create regions where planetary orbits see and be stable for billions of years, despite the apparent chaos of having several stellar gravitational sources. These stable orbital zones, called Lagrange points and Trojan regions, provide potential havens where planets can exist in gravitationally complex environments. Understanding the tidal dynamics of multiple star systems is crucial for assessing the habitability potential of planets in these common but complex stellar arrangements. As we continue this gentle journey through the stellar realm, let your mind drift along with the slow cosmic processes we've explored. Stars spinning in their patient rhythms, binary companions sharing material in graceful spirals, and ancient stellar remnants keeping precise time across the galaxy. Each fact we've discovered tonight adds another layer to the peaceful complexity of stellar existence. From the mineral clouds in cool stellar atmospheres to the magnetic fields that extend far beyond the stars themselves. The universe of stars continues its ancient dance around us, with processes unfolding on timescales that stretch from seconds to billions of years. Some stars are busy creating the elements that will one day become planets and life. while others are settling into long, quiet retirements as they slowly cool over cosmic ages. In binary systems throughout the galaxy, stellar partners continue their orbital waltzes, sometimes sharing material, sometimes triggering spectacular explosions, but always moving to the rhythm of gravity and time. These stellar processes continue even now as you rest, a reminder that the cosmos is filled with gentle, ongoing activity that requires no observation to persist. Stars are pulsing with their internal sound waves, stellar winds are carving cavities in space, and somewhere in a distant molecular cloud, new stars are beginning their slow journey toward ignition. Somewhere in the darkness between stars, cosmic recycling continues its ancient work. When stars shed their outer layers or explode in supernovae, they don't simply vanish. Their material becomes part of vast, slow-moving currents of gas that drift through the galaxy for millions of years. These stellar exhalations mix and mingle in the interstellar medium, carrying with them the chemical legacy of countless stellar lives. Elements forged in stellar cores spread outward at speeds measured in kilometers per second, eventually reaching regions where new stars will form. This cosmic circulation system operates on timescales so vast that individual atoms may spend hundreds of millions of years drifting through space before becoming part of a new stellar generation. The iron in a distant star may once have been part of a supernova explosion that occurred when our galaxy was young, while the carbon atoms in a newly forming planetary system may have originated in the gentle winds of red giant stars that died billions of years ago. Some stars possess atmospheres so extended they could engulf entire planetary systems. Among the largest stars in the universe are objects whose atmospheres are more tenuous than any vacuum we can create on Earth, yet extend across distances measured in astronomical units. These hyperextended stellar atmospheres occur in certain types of evolved stars, where stellar winds have inflated the outer layers to incredible dimensions while maintaining only the faintest densities. A planet orbiting within such an atmosphere would experience conditions unlike anything in our solar system, bathed in stellar material while still receiving direct starlight from the star's distant core. The atmospheric material would be so thin as to be nearly imperceptible, yet its presence would create subtle effects on any orbiting bodies, from atmospheric drag to chemical interactions. These stars challenge our conventional notions of where a star's surface ends and space begins, existing as gossamer giants whose influence extends far beyond their visible boundaries. The oldest stellar populations in our galaxy tell stories of cosmic youth. Deep in the galactic halo, ancient stars continue to burn with the chemical simplicity of the early universe. These stellar time capsules formed when the Milky Way was still assembling itself from smaller building blocks, and their atmospheres preserve the chemical conditions that existed billions of years ago. Unlike younger stars that show evidence of multiple generations of stellar nucleosynthesis, these ancient suns contain almost no elements heavier than hydrogen and helium than lithium, reflecting a time when the universe had not yet been enriched by the products of stellar evolution. Studying these primitive stars is like reading the universe's earliest chapters, written in the language of spectral lines and abundance ratios. They move through the galaxy on orbits that reflect the chaotic conditions of early galactic assembly, following paths that take them far above and below the orderly disk where younger stars like our Sun reside. Stellar magnetic activity can create auroras on planets orbiting distant stars. Just as our Sun's magnetic field interacts with Earth's magnetosphere to create the beautiful aurora displays we see at high latitudes, other stars throughout the galaxy likely create similar phenomena on any planets that orbit within their magnetic influence. Stars with particularly strong magnetic fields and active coronae can generate stellar flares and coronal mass ejections far more powerful than anything our Sun produces. When these energetic events interact with planetary magnetospheres, they could create aurora displays of incredible intensity and beauty, potentially visible even on the daylight sides of affected worlds. Some exoplanets orbiting very close to their host stars might experience nearly continuous auroral activity, creating permanent light shows in their upper atmospheres. These stellar planetary magnetic interactions also play important roles in atmospheric evolution, potentially stripping away atmospheric material from planets that lack strong protective magnetic fields, while simultaneously delivering energy that could drive atmospheric chemistry and potentially even biological processes. The formation of the heaviest elements requires the most extreme stellar environments. While ordinary stellar fusion can create elements up to iron in the periodic table, the synthesis of gold, platinum, uranium, and other heavy elements requires conditions so extreme that they exist only in the most violent stellar events. When neutron stars collide, or when the most massive stars undergo core collapse, the incredible densities and temperatures briefly recreated conditions similar to those that existed in the first moments after the Big Bang. During these fleeting instants, atomic nuclei are crushed together with such force that they can capture multiple neutrons in rapid succession, building up the heaviest elements through processes that cannot occur anywhere else in the universe. These cosmic alchemical laboratories operate for mere seconds or minutes, but they produce enough heavy elements to enrich entire regions of space. The gold in jewelry, the platinum in catalytic converters, and the uranium in nuclear reactors all trace their origins to these moments of stellar violence, making every heavy element on Earth a memento of cosmic catastrophe. Some binary stars create their own eclipsing rhythms that can be detected across vast distances. In binary systems where the orbital plane is aligned with our line of sight from Earth, we can observe regular eclipses as one star passes in front of its companion. These eclipsing binaries create precise periodic variations in brightness that can be measured with extraordinary accuracy, sometimes revealing changes of less than 1% in the total light output. The eclipse patterns carry detailed information about the sizes, shapes, temperatures, and orbital characteristics of both stars, allowing astronomers to determine stellar properties with remarkable precision. Some eclipsing systems show additional complexities, such as ellipsoidal variations caused by tidal distortions or reflect ion effects where one star heats the facing hemisphere of its companion. The most exotic eclipsing binaries involve compact objects like white dwarfs or neutron stars, creating eclipse patterns that reveal the extreme physics operating in these dense stellar remnants. These natural stellar laboratories provide some of the most precise measurements possible in astronomy, turning distant binary systems into cosmic precision instruments. Cool stellar atmospheres can develop complex molecular chemistry resembling planetary atmospheres. In the coolest stars, where surface temperatures drop below a few thousand degrees, conditions become favorable for the formation of complex molecules that would be destroyed in hotter stellar environments. These cool stellar atmospheres can contain water vapor, carbon monoxide, methane, and even more complex organic molecules, creating chemical environments that share some similarities with planetary atmospheres. The molecular chemistry in these stellar atmospheres affects how the stars radiate energy, creating absorption bands in their spectra that reveal the presence of specific molecular species. Some of the coolest brown dwarfs show evidence of weather systems driven by the condensation and evaporation of exotic clouds made from materials like iron and silicate minerals. These atmospheric dynamics create temporal variations in brightness and color as cloud systems rotate in and out of view, making these objects resemble planets as much as stars in their behavior and properties. The space between binary stars can become a laboratory for extreme plasma physics. In close binary systems where material flows from one star to another, the region between the stars becomes filled with hot, ionized gas moving at tremendous speeds. This interstellar plasma experiences magnetic fields, radiation pressure, and gravitational forces that create conditions impossible to replicate in terrestrial laboratories. The flowing material can form complex structures like magnetic towers, plasma jets, and shock fronts, where different streams of stellar material collide. These plasma environments can accelerate particles to enormous energies, creating cosmic ray sources within our own galaxy. The interaction between stellar winds, magnetic fields, and transferred material creates a constant, changing plasma landscape that varies on timescales from minutes to years. Understanding these binary plasma environments helps astronomers comprehend some of the most energetic processes in the universe, while providing natural laboratories for studying plasma physics under conditions of extreme temperature, density, and magnetic field strength. Ancient globular clusters preserve samples of the galaxy's earliest stellar generations. Scattered throughout the galactic halo are dense spherical collections of stars called globular clusters, each containing hundreds of thousands of stars packed into regions only a few dozen light-years across. These stellar cities are among the oldest objects in our galaxy, with ages approaching the age of the universe itself. The stars within globular clusters formed from the same primordial gas cloud, giving them nearly identical ages and chemical compositions, while creating natural laboratories for studying stellar evolution. Because all the stars in a cluster formed at the same time, astronomers can observe stellar evolution in action by comparing stars of different masses within the same cluster. The most massive stars have long since evolved into white dwarfs or neutron stars, while the smallest red dwarfs continue burning essentially unchanged since the cluster's formation. These ancient stellar communities have survived billions of years of galactic evolution, maintaining their identity while orbiting through the galaxy's gravitational field. Stellar rotation can create magnetic dynamos that power continuous stellar activity. Many stars generate magnetic fields through dynamo processes driven by the interaction between stellar rotation and convective motion in their outer layers. These stellar dynamos can operate continuously for billions of years, creating magnetic field cycles similar to our Sun's 11-year solar cycle, but often with very different timescales and intensities. Some stars show evidence of magnetic cycles lasting decades or even centuries, while others appear to maintain constant levels of magnetic activity throughout their lifetimes. The strength and configuration of stellar magnetic fields affects many aspects of stellar behavior, from the production of stellar flares and coronal mass ejections to the rate at which stars lose mass through magnetized stellar winds. Stars with particularly strong magnetic fields can maintain active chromospheres and coronae that emit substantial amounts of high-energy radiation, creating space weather environments around these stars that could significantly impact any orbiting planetary systems. The chemical fingerprints of stars reveal the history of galactic mergers and interactions. When small galaxies are captured and disrupted by larger ones like our Milky Way, their stars become scattered throughout the larger galaxy's halo and disk. These accreted stars often retain chemical signatures that differ from stars born within the host galaxy, allowing astronomers to identify stellar populations that originated in other galaxies. By studying the chemical compositions and orbital motions of thousands of stars, astronomers can reconstruct the merger history of our galaxy and identify the remnants of ancient galactic meals. Some stellar streams in the galactic halo are the stretched-out remains of globular clusters or dwarf galaxies that were torn apart by tidal forces, while other stellar populations show the chemical signatures of different galactic environments. This stellar archaeology reveals that our seemingly stable Milky Way has grown through countless mergers and interactions over its billions-year history, gradually accumulating stellar populations from smaller galaxies that ventured too close to its gravitational embrace. Binary evolution can create stellar objects that exist nowhere else in the universe. The complex interactions between stars in binary systems can produce exotic stellar remnants that have no counterparts among single stars. When white dwarf stars accrete material from companions, they can undergo thermonuclear explosions that either destroy them completely or leave behind unusual stellar products with properties unlike any single star evolution can produce. Some binary interactions create helium stars, objects that have been stripped of their hydrogen envelopes by companion stars and burn helium directly in their cores. Others produce carbon-oxygen white dwarfs with unusual compositions, or neutron stars with magnetic fields and rotation rates that reflect their binary origins. These binary-produced objects often have properties that lie between the normal categories of stellar evolution, creating a zoo of exotic stellar remnants that exist only because of the complex gravitational and mass transfer processes that operate in close binary systems. The most distant stars we can observe individually are cosmic lighthouses from the early universe. With our most powerful telescopes, astronomers can detect individual stars that are so far away. Their light has been traveling toward us for most of the age of the universe. These incredibly distant stars are typically the most luminous objects of their kind. Massive blue giants, or explosive stellar events that can outshine entire galaxies for brief periods. Observing these ancient stellar beacons provides direct information about star formation and stellar evolution in the early universe, when galaxies were younger and the chemical composition of the cosmos was very different from today. Some of these distant stars show evidence of unusual chemical compositions or evolutionary pathways that may no longer exist in the modern universe. Their light carries information about cosmic conditions that existed when the universe was a fraction of its current age, making each detected photon a messenger from a time when the cosmos was still young and rapidly evolving. Stellar winds from the most massive stars can affect galactic evolution on large scales. The most massive stars in any galaxy produce stellar winds so powerful they can influence the structure and evolution of entire galactic regions. These winds carry away significant fractions of the star's mass, while also sweeping up and heating the surrounding interstellar medium. Over the lifetimes of massive star populations, their collective winds can blow away gas from star-forming regions, regulate the rate of future star formation, and even drive galactic-scale outflows that carry material into intergalactic space. In smaller galaxies, the combined effect of stellar winds from massive stars can be so significant that it affects the galaxy's ability to retain gas and continue forming stars. This stellar feedback process helps regulate galactic evolution and may explain why some galaxies stop forming stars despite having abundant gas supplies. The winds from massive stars thus play a crucial role in the cosmic cycle of star formation and galactic evolution, connecting the lives of individual stars to the evolution of entire galactic systems. Variable stars can serve as natural experiments in stellar physics. The regular pulsations and brightness changes exhibited by various types of variable stars provide astronomers with natural laboratories for testing theories of stellar structure and evolution. As these stars expand and contract, their internal conditions change in predictable ways that can be compared with theoretical models of stellar behavior. The precise timing of pulsational variables reveals information about stellar masses, internal structure, and evolutionary state that cannot be obtained through any other observational method. Some variable stars show complex pulsation patterns with multiple periods operating simultaneously, creating interference patterns that reveal details about different layers within the stellar interior. These stellar oscillations are driven by the same physical processes that govern the structure of all stars, making variable stars cosmic test cases for our understanding of stellar physics. By studying how these natural stellar experiments respond to changes in their internal conditions, astronomers can refine their theories of stellar evolution and improve their understanding of how all stars live and die. The end of stellar nucleosynthesis marks a fundamental transition in cosmic evolution. As the universe ages and the supply of hydrogen fuel gradually becomes depleted, the era of active star formation will eventually come to an end. This transition will mark one of the most significant changes in cosmic history since the formation of the first stars billions of years ago. When star formation finally ceases, The universe will enter a new phase dominated by stellar evolution rather than stellar birth, as existing stars gradually burn out without being replaced by new ones. The last stars to form will be the long-lived red dwarfs, which will continue burning for hundreds of billions of years after star formation ends. During this extended twilight period, these final stars will be the universe's last sources of nuclear energy, slowly converting the remaining hydrogen into helium while the cosmos around them grows increasingly cold and empty. This stellar twilight will persist for timescales that dwarf the current age of the universe, representing the final chapter in the story of stellar nucleosynthesis that began when the first stars ignited in the primordial darkness. And now, as our gentle journey through the stellar realm comes to a close, let your thoughts drift like starlight through the cosmic darkness we've explored together. We've wandered among pulsing variables keeping time in the void, witnessed binary companions sharing their very essence across space, and discovered how the smallest stars will outlive everything else in the universe through their patient burning. Each stellar fact has been a soft reminder that above you right now, countless suns continue their ancient work, some crystallizing into diamonds, others breathing with sound waves, all participating in the grand cosmic recycling that connects every atom in your body to the heart of a distant star. May these peaceful truths about stellar life accompany you into sleep, and may your dreams be as gentle as the light from red dwarfs that will shine long after all else has faded into cosmic night.